Let's jump right into this explainer. I want you to picture something straight out of sci-fi that is actually rapidly becoming reality. Imagine a team of robots seamlessly cleaning your house, or a robotic construction crew building a structure, or even just two machines effortlessly moving a heavy couch through a narrow doorway. Sounds incredible, right? But behind that dream lies a massive, real-world engineering nightmare. Getting multiple autonomous machines to just work together as a team without colliding, stalling, or dropping what they're carrying, well, it's literally one of the most complex challenges in modern robotics.
So why is it so hard for robots to carry a couch together? To really get this, think about how you and a friend would move some heavy furniture. You pick up your end, they grab theirs. You're definitely not shouting out the exact angle of your elbows or the precise force of your grip, right? You rely entirely on intuitive, silent cues. A slight shift in weight, a quick glance, maybe a subtle nod. Your brain processes all these visual and physical signals instantly, letting you react and adapt on the fly. For us humans, this silent, reactive coordination is just second nature. But for a machine, replicating this kind of silent intuition is remarkably difficult.
And that brings us to the core problem. While human teamwork is based on those intuitive visual cues and independent action, traditional robot teamwork has typically relied on a completely different philosophy: centralized micromanagement. In your standard multi-robot setup, you usually have a single master computer. This central brain tries to constantly ingest camera feeds from every single robot, crunch the math for every single joint, and then send out perfectly synchronized commands. As you can probably guess, the second you add more robots to the team, you create a massive data bottleneck. It's kind of like having a team where no one is allowed to take a single step until a manager explicitly calculates the exact position of everybody's feet. Total nightmare, right?
Section 1. Meet the cast and the chorus solution.
Okay, let's dive into this fascinating new research out of Stanford University that completely flips this paradigm on its head. They've developed the revolutionary framework called Chorus. But to understand how it works, we first need to meet the very unique robotic teammates they tested it on. On the left, we've got the Kinova robot featuring 11 joints, or degrees of freedom, and over on the right, the RX robot with 10. What you really need to notice here is that they have entirely different physical bodies, or what engineers call embodiments. They operate in completely different ways, and get this, they even process actions at entirely different speeds. In a traditional centralized system, trying to get two totally different machines running at different frequencies to perfectly synchronize, it's a massive headache.
To solve this, the researchers turned to a Vision Language Action, or VLA, backbone. If you're not super familiar with VLAs, just think of them as incredibly advanced AI brains. Similar to how large language models basically read the whole internet to learn how to write, VLA models are trained on massive amounts of text and video data to understand how the physical world actually works and how to perform physical tasks. These VLAs form the core intelligence engine behind the whole CHRS system.
So instead of one giant central brain acting as a puppet master over a network, Chorus takes a single VLA policy and deploys it for decentralized execution. Think of it like a sports team. Instead of the coach shouting out every single footstep to every single player during the game, the coach gives every player the exact same universally shared playbook to memorize before they even step onto the field. Once the game starts, the players execute their plays completely independently, using only their own eyes to see what their teammates are doing. Every robot has a copy of the Chorus brain locally. It's a real game changer.
Section 2. One brain, many robots.
Now, that raises a pretty fascinating technical question. If every robot is running the exact same software playbook, how on earth does the software know which robot it's currently operating? Well, the secret is surprisingly elegant. It all comes down to a simple text prompt. Before the AI generates an action, the system just feeds it a robot-identifying tag, like YAM or Kinova. Because this advanced VLA brain has seen so much diverse data during training, that single little text prompt is literally all it needs. It instantly says, okay, I'm currently wearing the Kinova body. I have 11 joints, and here's my specific role in this task. It allows one unified brain to drive completely different physical bodies without any confusion whatsoever.
When we compare this to traditional centralized systems, you can see exactly why this is such a breakthrough for scaling up robot teams. With a centralized system, every single time you add a new robot, the context window, which is the sheer volume of data the central computer has to process, just grows larger and slower. But with Chorus, that context window remains completely constant. Each robot only processes its own local camera feed, and because of that, absolutely zero communication is required between the robots while they're actually executing the task. No Wi-Fi lag, no dropping the network, just independent agents working together visually. Section 3. Putting Chorus to work.
Now, what's really interesting about this slide is seeing how this actually builds into real-world applications. The researchers didn't just run simple simulations. They set up incredibly complex physical tasks for these robots to accomplish together. Here in Task 1, the reactive book handover, notice the sheer precision required. The robot on the left is holding a book and moving it toward the kin of a robot on the right. And remember, they are absolutely not talking to each other over a network. The kin of a robot has to use its own cameras to watch the other robot's movements, predict its trajectory, and adjust its own arm in real time to successfully complete the grasp. It is purely visual teamwork.
Next up, we have the collaborative basket lift. Look, if you've ever tried to carry a heavy laundry basket with someone, you know that if one person lifts too fast or just moves off course, the whole basket tilts and drops. Here, the robots successfully manage to lift the basket in perfect harmony. They keep it completely level by perceiving their teammates' progress purely visually, dynamically adjusting their own grip and lift speed as they go. Task 3 pushes things even further with a mobile tape measure. This one is incredibly impressive because it requires cooperative tension. They aren't just mimicking each other's actions in empty space here. One robot actually has to firmly hold the base of the tape measure, while the other robot precisely extends the tape across the table. They are physically interacting with the exact same tool, relying entirely on the shared course AI to manage the push and pull without snapping the tape. But wait, this is the grand finale. To prove that this decentralization actually scales up, they brought in a third robot. So we've got 2 robots lifting and carrying a heavy laundry basket, while a third robot coordinates to open the door for them. The Chorus framework scaled seamlessly to this 3-robot team and hit a massive 90% success rate on this highly complex task. And you want to know the best part? They didn't even have to alter the AI architecture at all to make it happen. It just works. It is genuinely awe-inspiring to see these completely distinct machines coordinate so flawlessly.
Section 4. The data delivery and the future of collaboration.
Stepping back from the visuals for a second and looking into the hard performance metrics from the research paper, we find an absolute game changer. These numbers prove exactly why this specific framework is such a massive leap forward for the entire field of robotics. So, the crucial point is, when tested against standard, from scratch to centralized models that the industry currently uses, Chorus didn't just edge them out. No way. It achieved a staggering 64 percentage point improvement in task success rates. That's a huge jump.
And the secret to that massive leap in success? It's teammate reactivity. The researchers ran this really cool test where they explicitly bumped and perturbed one of the robots mid-task just to see how the other would react. When they used standard separate policies for each robot, the team only recovered about 45% of the time. But when using the shared course policy, where every single robot is running on the exact same underlying neural weights, that recovery rate literally skyrocketed to 85%. Because the AI was trained on the perspectives of all the robots, it essentially built an internal understanding of how its teammates behave, making it nearly twice as reactive to unexpected surprises.
Bringing it all together, this outlines exactly why Chorus changes the game. You only have to train and deploy one single policy, no matter how many robots you have on the team. You completely eliminate the need for a flawless communication network during the actual task. It effortlessly handles robots moving at entirely different speeds asynchronously. And as we just saw, it scales to larger teams without breaking a sweat. This research isn't just some small incremental step, it actively clears the path for highly capable multi-robot crews to finally leave the laboratory and enter our homes, our hospitals, and our construction sites.
Which leaves us with a truly profound thought to end on. We've spent decades trying to build perfect communication networks to get machines to work together. But this research shows that true collaboration might just be about silent observation and shared intelligence. If robots no longer need to talk to seamlessly collaborate, what will they build together next? Thanks so much for joining this explainer. I really hope it sparked your curiosity, and I'll see you next time.